Welcome everybody to the 936th monthly meeting of the Amateur Telescope Makers of Boston. For those celebrating tonight, happy Hanukkah. And we're glad you could make it. Let's begin. Well, tonight's guest speaker is Diana Heineken. She's going to talk about the radio sky, exploring the universe at the longest wavelengths. But before we get to her, of course, we'll do the business part of the meeting. And so let's see if I can do this. This is a cartoon from Glenn, alluding to December 21st. And everybody had an appropriate amount of time to chuckle.
Okay, can you hear me okay?
We can, Glenn. Yeah, you're on.
Yeah, I did a little research. I used to work at a planetarium. We did a program about the Star of Bethlehem, and there are a couple of theories. And one, just by coincidence, it turns out that there is a thought that around 7 BC, there was a triple conjunction of Jupiter and Saturn, those two planets. There's another one, I think it was Jupiter and Venus, perhaps, around 2 to 3 BC, somewhere in there. But anyway, it's going to be a very interesting event. I'll talk about that in just a minute. We'll go to the next slide. Whatever else astronomy may or may not be, who can doubt it to be the most beautiful of the sciences? I know geologists and meteorologists will disagree, but when you look at pictures of some of our club members like Mario and Doug Paul and so forth, it is, to me, it is the most beautiful science. Whatever's up there, it's Saturn, for instance. Can't beat that. And I even put that over a quartz crystal. Sorry, geologists. Next slide. Okay, what's going on between now and the next meeting? First of all, on Saturday, December 12th, which is coming up, in the morning, Venus will pair up with a waning crescent moon. Venus will be below the moon, and you're going to have to look pretty much in the southerly sky, again, a little bit before sunrise. On the 13th to 14th, we have the year's most prolific meteor shower, the Geminids, and it'll be after sunset Sunday and continuing until Monday morning on December 14th. The moon won't be a problem. The moon will be near new moon, so we won't have any problems with that. And at maximum, we should be able to see upwards of 120 meteors. Again, that depends on if you're in a dark sky location or not. And I guess the peak activity is going to be right after midnight, and we'll be in that window. Last time, I think, around, it was more in Asia, another part of the world that had the real maximum of the Geminis, but we're going to get the front row seats. So cross our fingers that the weather cooperates. We'll pass on Monday, December 14th. That's going to cause a lot of anguish and anxiety here, but some people will get to see that eclipse and enjoy it. Maybe we'll just look for images on the internet. On the 21st, winter solstice. And again, that's probably good news for the people that hate long nights. Bad news for us because it means the days are going to start getting longer again. And by the way, I believe we just had our earliest sunset a few days ago. The sunset is actually going to start setting a little bit later. And I noticed that years ago when I was really doing a lot of variable stars that after the 6th of December, thereabouts, all of a sudden I noticed that sun's setting a little bit later. You really notice this and you don't want to get out right at sunset. So that's coming up. On Monday, December 21st, right after sunset, this is the big one. And this is pretty much, it definitely is a once in a lifetime event as far as seeing these things so close together. They're going to be just 6 arc minutes apart. So even in a high power view of a telescope, you'll be able to put them together. The only problem is it's going to be very low in the southwest. So I suggest you start looking now, check to see where they are, find a location where you see them, because you certainly don't want to miss that on that particular night. They should be even really nicely close to a few days before and after. So we want to see it at that time. But if we get clouded out, a day or two afterwards, it should still be very spectacular. The last time they were this close that we could see them in the sky was about 800 years ago. And there's several centuries before they'll be this close again. Next slide.
Let me just say a couple of things about that, Glenn. They on the 21st, they transit at about 3 o'clock in the afternoon. And so my plan is to start looking, I like to find things in the daytime.
Yeah.
And so I've already started to practice finding Jupiter in the daylight. And hopefully I'll be ready to scoop it up that afternoon. But you're right, for a couple of days before and after, both planets will fit within a 1 degree eyepiece field. So they'll be close together for quite some time. But you're right; it's a pretty rare event, and yeah, you don't want to miss that one. All right, let's go to the next slide.
The Ursus meteor shower. This is one that's kind of on my bucket list. It's not a major shower. You might see about anywhere from 5 to 10 every hour. It radiates near the star Kokab, which is in the bowl of the Little Dipper. And it's pretty much an all-night event. You'll be able to start seeing these meteors right after sunset. The moon will be at first quarter, so after midnight, there should be no problem with that. It'll be out of the way. This is one, again, I have gone out and looked for it before, and I just wasn't patient enough. I seem to recall looking at about 5 minutes at one time and then 5 minutes another, not seeing anything. You got to really get bundled up and just go out and give it a little bit of a try. See if you can, even if you catch a couple of them, you can say you've notched that particular meteor shower. On January 2nd, Earth is at perihelion, 91.5 million miles from the sun. And again, we'll be at our farthest from the sun on around July 4th next year. On January 3rd, in the early morning, the Quadranted meteor shower. And this is actually pretty much as prolific as the Gemini is. It's just that it's more the actual peak is just a matter of hours. So if you hit it right, you can see upwards of 100 to 120 meteors in an hour. But again, we won't have that opportunity this year just because the moon will be waning gibbous. So it's going to kind of muck that particular shower up. And then finally, on January 9th, I believe that'd be the day before our next meeting, Jupiter, Saturn, and Mercury will be clustered very low in the west-southwest sky. If you thought it was tough to see Jupiter and Saturn on the 21st, it'll be even worse at this particular time. But if you have a very low west-southwest horizon, you might want to check this out, especially with binoculars, about 30 minutes after sunset. Next slide. Our observer's challenge for this month is a Messier object, M76, the Little Dumbbell Nebula in Perseus. And you can see its location. It's actually conveniently located near Omicron, or 5 Persei, and that's around 4th magnitude star or thereabouts. So all you have to do is basically just ring up that particular star, and you're going to find it. And the Little Dumbbell is one of 4 Messier objects that are planetary nebulas, the other being M27, the Dumbbell, M57, the Ring, and M97, the Owl Nebula. And this one is considered, just from the readings I was doing on this, they consider this one of the tougher Messier objects to look at. I saw it with a 3-inch telescope, 3-inch reflector years ago, and I don't recall it. It was definitely faint with that little scope, but I didn't think it is, I still found it easier than a lot of these fainter galaxies in the Coma Virgo cloud. So, but it still is a little bit of a challenge. You certainly want to save it for a nice dark night, especially if you're using a small aperture scope. Next slide. And we have some images. The one on the left is from Mario, the one on the right is from Doug Paul. And I don't know if Rich can point this out. They're getting the outer parts of that nebula. And you notice it seems to be going from the lower left to the upper right. But if you look in the bright area in the middle, it's just the opposite. It's going, that's the area that most of us see with a small telescope. That's what I saw with my little 3-inch scope. So it'd be interesting to see what aperture you need to start to see some of the outer nebulosity of that particular object. It's about 2,500 light years away, and what you're looking at is something that's a little over a light year across. It was discovered by Pierre Méchain in 1780. He saw it in September of that year, and he reported to Messier, who cataloged it about a month later. So again, it's a little brighter than what we've been getting. Again, it's one of the fainter of the Messier objects, but this would be a fun one to look for when you get a nice clear night. Again, very easy to find because it's just within a couple of footsteps of 5 Persei. Next slide. All right, this is Mario's favorite variable star. It's one of mine. David Levy loves this one too. This is the light curve for SS Cygni, which we talked about last month. And around the middle of that, that's the outburst that we are all looking for. It went up to about 8th magnitude, and then it settled down, and Rich can show there's a lot of bouncing around, but it came up earlier than was expected. It usually has an outburst every 50 days. But the first one, the one in the middle there, occurred around October 1st. That was maximum. And the maximum of this most recent one was just at the end of October. So we're talking about a 30-day stretch between. The star now, the most recent observation, just down around 11th magnitude again. As before, it's never too late. The Cygnus is still high in the sky in the evenings, and I've been able to follow SS Cygni right into February because it's in the upper corner of Cygnus, so it sets along after the main constellation disappears below the horizon. So if you have a nice area in the northwest, you can follow this star till February. So I would guess that there'll be another outburst of the star before it finally goes bye-bye until, again, later on in the year when it comes back in the evening sky. Next slide. Couple of pictures that we didn't get to show last time. Over on the left is that picture of the triangle I've been talking so much about with 3 stars, 8.6, 9.8, and 9.6. That's a triangle that I was able to see with my little 3-inch reflector years ago when I saw my first outburst of SS Cygni. And this is a picture that was taken by Joseph Rothschild, and it shows SS Cygni at outburst, and it's circled there in that little yellow circle. And again, it's a really neat star. If you've been watching this night after night and it's sitting at around 11th, 12th magnitude, and then if you're lucky, you see it on the way up. Most times, one night it's 11.2, the next night it's up at around 8.5, just overnight. The outbursts are very quick usually. Again, it's an unpredictable star. And next, again, a couple of slides wasn't able to show last time. These are taken by Doug Paul. And on the left is SS Cygni before outburst in its quiescent stage. And then on the other side, during an outburst, look at the bluish color of that star. But again, as I mentioned last time, if you kind of look back and forth, just look at SS Cygni in one picture and then the other back and forth, you see how it seems to blink on and off. Again, it's a great variable star, and I'd encourage you to give it a look-see, especially since we have a couple of more months before it finally fades out of sight. I think that's it.
I think so, Glenn. Let me just double check.
Yep.
Yep. Thank you, Glenn.
Well, as always, keep looking up, and we'll see you next month. And as Rich said, happy Hanukkah, Merry Christmas, and a Happy New Year. And let's get through this COVID thing soon. Thank you.
We will. Well, if there's nothing else, then let's go to our speaker for this evening. Diana, I'm going to stop sharing my screen, and that will allow you to share your screen. And I will introduce her while she comes online. Dr. Diana Heineken is our featured speaker tonight. And from her bio, I learned that after attending the University of Edinburgh for her undergraduate studies, Diana earned a PhD in high energy astrophysics from the University of Helsinki. I found it interesting that during her PhD studies, she was able to flip the seasons, and by visiting the University of Sydney, where she made observations, X-ray and radio observations of the X-ray binaries, which are dubbed microquasars. She's currently the observing editor at Sky and Telescope and a dear friend of the ATMoB. Her presentation this evening is titled The Radio Sky, Exploring the Universe at the Longest Wavelengths. So let's please give her a warm ATMoB welcome. I know everybody's muted, but Diana, thank you for being here with us tonight. I'm going to mute myself.
There we go. I see the controls are up here as well. Okay, perfect. Hang on a minute. I was hoping to get presenter view. Let me get that up and going. Okay, here we are. Hello, everybody. I'm thrilled to be here on the last meeting of your year. And as Rich said, the title of my talk was The Radio Sky, Exploring the Universe at the Longest Wavelengths. But as I was preparing this talk, I suddenly started going down this rabbit hole of exploring the history of radio telescopes, how they came about, and the different observing techniques, and bringing us to where we are today. And so I kind of amended the title a little bit. And so it's The Radio Sky, How Do We Explore the Universe at the Longest Wavelengths? So I think we need to start by saying RIP to rest in peace, Arecibo. We all know that this tragic thing happened earlier this month, but it was since August that this magnificent structure had started failing with the collapse of the cables and all of that. And then finally on December 1st, the whole the whole carriage with the at the secondary focus just came crashing down and completely crushed the dish. So as we commemorate the history of radio astronomy and the beauty of radio telescopes, let's remember all the people who have worked at Arecibo and all the effort that they put into making that such an amazing facility. So I'm sure many of you are familiar with the various radio sources that we have in the sky in the universe. Let me get a pointer up. Our closest star, the sun, is a radio emitter. We have pulsars, rapidly rotating neutron stars that emit particles, jets of particles at relativistic speeds, and they spin rapidly. Whenever the beam of particles swings towards our line of sight, we get a pulse of radiation. And these are strong radio emitters, as is the Milky Way. This is a map of the Milky Way. The planets are radio emitters. The part of the radio universe is, of course, the cosmic microwave background, and this is a lovely map put together by the Planck collaboration. And of course, we have quasars, where you have a galaxy, a host galaxy with a supermassive black hole at the core, accreting matter from its host galaxy, and then spewing that matter out again at relativistic speeds in two opposite directions that we see as radio jets. The galaxy is visible as usually an optical target, and then these radio jets that extend for hundreds of thousands of light years are very strong, are seen in the radio. And then, as Rich mentioned, microquasars, which was my field, where you have small scale analogies of the extragalactic quasars, but instead of a supermassive black hole, you have a stellar mass black hole accreting matter from a companion star, but you see exactly the same morphology. You have black hole accreting matter and then spewing that matter out in, well, not the black hole, but from the accretion disk, from the inner parts of the accretion disk, the matter gets spewed out in bipolar jets. So these are all radio emitters, and we know, we've been exploring the radio sky for a while, but before that, before about 1930, most of the information that we garnered from the universe, or practically all of it, was in the visual wavelength region. Until the 1900s, most of what we knew that was out there was planets, stars, open clusters, globular clusters, various types of nebulae. Some catalogs were compiled to try and keep track of what all these objects were. And there were some early experiments in infrared techniques towards the end of the 1800s, but the challenges posed by Earth's atmosphere were just too much. So infrared astronomy also had to wait until the 20th century. And then around the 1910s and 1920s, we started to understand that there was a lot more universe out there, particularly with the studies by Edwin Hubble and his assistant, Milton Humason, in cataloging the redshifts of a bazillion galaxies and coming up with the redshift distance correlation. So most of what we knew about the universe came from these magnificent instruments. And a lot of it toward the 1800s then, much of that information was recorded on photographic plates. So in the late 1920s, a young physicist and engineer by the name of Karl Jansky was employed by the Bell Telephone Laboratories, and his task was to investigate the sporadic static that could interfere with the radio communications that was a nascent field at the time. And so to do this, he built a telescope that was mostly brass piping and timber, and it was some 30 meters or about 100 feet across. And he mounted this contraption on the wheels of a Model T Ford. And so the whole thing could rotate fully every 20 minutes was his technique. He just rotated every 20 minutes. And of course, inevitably, it earned the nickname Jansky's merry-go-round. Everybody knew it as Jansky's merry-go-round. So he was able to identify 3 types of interference that were messing about with their radio communications there at Bell Lab. And he identified local thunderstorms, and he identified in the signals that he was receiving, he identified distant thunderstorms. But then there was also a steady hiss type of static of unknown origin, according to his paper. Now, I'm just going to pause here for 1 second and just remind everybody, we have right here in front of us, we have Jansky's merry-go-round that is about 100 feet across. And you might ask, why do we need something that is so large? And just to remind everybody, when we have the electromagnetic spectrum, we are all used to seeing the visible. Our eyes are adapted, we see the visible, but beyond the visible, we have the shorter wavelength bands of the electromagnetic spectrum. As we go to shorter and shorter wavelengths, we go from ultraviolet to X-rays to gamma rays. As we go to shorter wavelengths, we go to higher energies. And as we go to longer wavelengths, on the longer wavelength side of the visible spectrum, we go from infrared to progressively longer wavelengths of the microwave and to the longest wavelengths that we know, that we call the radio. So one aspect of observing is resolution. Angular resolution is directly a function of the wavelength over the diameter of your instrument, the instrument that receives your radiation. So the longer the wavelength, the longer or the wider your apparatus needs to be able to identify detail in your observations. So that was just a little aside to show you what we're talking about. We're talking here in the radio, we're talking, the wavelengths are of the order meters to kilometers. And one incredibly fortuitous aspect of radio waves is that the majority of radio waves from outer space penetrate through Earth's atmosphere. And so we can place these big telescopes here on the ground and receive this radiation from outer space, unlike X-rays and gamma rays that you need to launch detectors into space, into orbit. And for the optical and infrared, where if you're not launching detectors on orbiting satellites, you're placing them on top of high mountains. So the one redeeming factor of radio is that the radio waves do come all the way through the atmosphere to the ground. So that was just a little aside. We're going back now to Jansky's merry-go-round. And in a paper that he wrote and published in 1933, he shows a plot of the data that he got with his instrument. And here on the x-axis, we have time increasing to the right, and we have the relative intensity of the radiation plotted here on the y-axis, increasing upward. And here on the top as well, we have the direction of where the radiation is coming from. And as I mentioned before, his whole merry-go-round rotated once every 20 minutes. And lo and behold, once every 20 minutes, we see a spike in the radiation, in the intensity. And these spikes corresponded to times when his merry-go-round was sweeping past or past the galactic plane. And he further plotted the azimuth of the direction of arrival for any particular day against the time of day. And as you can see here, hang on a minute, here we go. So so what he did was he plotted the months from January to, he missed November. So 11 is actually December. And so he plotted the time of day and against the direction of arrival. As you can see, there is a change in the azimuth of the direction. It changes gradually and uniformly through nearly 360 degrees during 24 hours. So that's following the blue arrows. Furthermore, there's a progressive shift as you go from January to February to March to April to May to June, all the way across. You come right back at the end of the year, you're back at the same spot where you started. Let me specify, at the end of the sidereal year, you're back at the same spot where you started. And so this, in Jansky's own words, were, to one familiar with the manner in which the heavenly bodies change their positions hourly and daily, these facts indicate that the direction of arrival is fixed in space. So this was the first time that a scientist had pinpointed the radio waves from outside of Earth's sphere. His discovery, sorry, I was going to use a pun here, made a lot of waves. There was a lot of publicity on his discovery. There was a lovely piece in the New York Times on May 5th of the year of publication. And they described his results, and he himself pointed out that the signal was strongest in the direction of the galactic plane, as we saw in those intensity curves. And he pinpointed the right ascension of the peak of the intensity at 18 hours of right ascension, which is somewhere in Sagittarius. And this coincided with the center of the Milky Way. Of course, at the time, they did not, scientists, astronomers did not know of the existence of the supermassive black hole that is at the center of our Milky Way. But now we know Sagittarius A star is there and is the source of lots of radiation, including radio. So in spite of all this publicity, his discovery failed to rustle up a lot of interest. At a conference barely 2 years after he published his discovery, there weren't even 24 people sitting in attendance to listen to this talk. And yet it was a phenomenal discovery. I mean, for the first time, we were getting a signal, a radio signal from outer space, but it just couldn't rustle up the interest. However, we honor this amazing pioneer in radio astronomy because we call the unit for flux density, we know it as the Jansky. There were other pioneers at the time. They weren't as, let's see, they were pretty creative. They came up with lots of fun ideas and innovative ideas of how to try and capture radio signals. And this is one of my favorites. This is John Krauss, who was a physicist. And he and his PhD student would ride around in his old car, his 1923 Studebaker, simply with a 3-meter aluminum rod poking out the top. And they'd ride around for hours. So he'd be driving and his student would be sitting in the back here with all the receivers and recording all the signals that they were getting. And he describes in his book, a fantastic book that's called Big Ear, where he went on, John Krauss went on to build one of the pioneering radio telescopes in the US at Ohio State University that was called Big Ear. And in the book Big Ear, he describes his early endeavors to capture radio signals. And so this was one, and in another one, he built this antenna that theoretically is about 100 meters long, but because it could fold, it only occupied a space of about 30 meters. However, in spite of the non-interest on behalf of many of the other scientists and astronomers, some people did have their ear to the ground when it came to Jansky's discovery, and it piqued their curiosity. And one of them was Grote Reber. He was an electrical engineer and amateur radio operator, and he was so inspired by Jansky's discovery that he built a parabolic dish, the first of its kind, in his backyard. It was about 9 meters across. And in fact, he was only the second person after Jansky to make radio astronomical measurements. And his dish, as I mentioned, was the first used in such a manner. He was pretty much the only active radio astronomer from 1937 to after World War II. There's one exception that I'll touch on in a minute. But in exploring Jansky's phenomenon, Reber wittingly or unwittingly mapped radio emission from large swathes of the Milky Way, effectively conducting the very first sky survey in the radio. And here is an example from his paper that we actually published in Sky and Telescope in April 1949. And we see these peaks of intensity here. And he identified them as coming from the galactic center, coming from an area in Cygnus, and coming from an area in Cassiopeia. So with this parabolic, with Reber's dish literally in his backyard, we start to see a little bit of a shift in design in terms of radio telescopes. We're going from the spindly Jansky merry-go-round types to these parabolic dishes. So World War II interrupts much activity on this planet, including astronomy and science. And but the one exception was that radar technology was being investigated and was developing in leaps and bounds. And the Brits, the Aussies, and the Americans were all heavily involved in, and the Germans as well, but we're all heavily involved in radar technology. And here are just some examples. This is a British radar. The Aussies had a slightly different design. And Americans were also exploring possibilities of installing radar devices on planes, for example. So the one exception to what I was saying about Reber being the only radio astronomer for almost a decade after 1937, there was this one exception. This was British physicist James Stanley Hay. He wasn't strictly a radio astronomer though, but his job was to monitor the Germans' radar jamming activities, and he did that on the cliffs of Dover with a mobile unit. And during February 27th and 28th of 1942, he could not understand there was this widespread daytime jamming of anti-aircraft radar. And he scratched his head quite a lot to try to figure out what it was. And the interference was of such an intensity that radar operation was virtually impossible. And he realized, he was a clever chap, and he realized that the direction of the maximum interference over those 2 days, two days that this was happening, that the direction followed the sun. So he got in touch with the Royal Greenwich Observatory, and they informed him that there was an active sunspot system that was transiting the solar disk. And this is an image taken from the Royal Observatory at the Cape of Good Hope in South Africa from exactly those dates, February 27th and 28th. So right after the war, there's almost an explosion in radio astronomy. A lot of these obsolete radar units were repurposed, and among the folk who immediately jumped at the opportunity to start doing something with these disused radar contraptions were a bunch of Aussies. Oh, did it not say that? Okay, a bunch of Aussies down near Sydney. There was Ruby Payne Scott and her collaborators, Joe Pawsey and Lindsay McCready. And what they did was they pioneered a technique called Seacliff Interferometry. And so the way this works is that you have a radar, like an antenna, like this one here, atop a cliff. And then you have the sea, and then you wait for the sun to rise. And as the sun rises, the antenna atop the cliff receives both the direct ray from the sun as well as the reflected ray, the ray from the sun that sort of bounces off the surface of the sea. And so the antenna on top of the cliff receives both these signals, but it actually, the reflected path actually acts as a sort of replacement antenna down here, substitute antenna down here. So in fact, what we end up with is a baseline, as we call it, of nearly 200 meters from where the antenna is actually on top of the cliff to where the path of the ray would have gone had it just been able to continue down to here. So basically the image of the antenna. And so they pioneered this method, and using that, they were able to identify the locations of sunspots on the solar disk. And they presented this paper in 1947 at a meeting of the Royal Society in London. And this is just an extract from that paper. Ruby Payne Scott was an interesting person. She was one of the only, if not the only, female in astronomy at that time, and she, because of the mores of those days, she had to quit her work once she got married. She was able to keep her marriage secret for a while, but when she got pregnant, then it was a little bit more difficult. And so sadly, she had to quit her work then. But her legacy will forever live on because she was definitely one of the people who pioneered the Seacliff Interferometry method. And now I'm just going to do a little aside here. As Rich said, yes, I went down to Australia quite a lot during my PhD studies, and then also during my time in research afterwards. And I was very grateful for that because this is pretty much what the view outside of my window looked like in January. And I would hop on a plane and I would get to Australia it was about 24 hours later, but it felt like about 398 hours later after all the flights and so on. And that would be the view from my digs in Australia. So I considered myself really, oh, hang on a minute. Oh my gosh, this is funny. Okay, so actually the picture on the left-hand side, oh, it looks as if I collect pictures of snow outside of windows. This is from my office here in Cambridge. So this makes me ask myself, is why I ask myself pretty often, why did I leave sunny Florida to come up to New England? Okay, I do have a collection of snow outside windows, I see now. Oh, Kelly, that's one of your spider plants, by the way. Okay, so anyway, this could be Finland though. I have a similar picture of Finland. So Finland, January, horrible. Go to Australia, this view, lovely. And the Aussies were big pioneers in radio astronomy. This is the Mills Cross at a place called Molangle outside of Canberra. And it was built in 1954. And it was basically two wire meshes that extended for several hundred meters in this cross-shaped pattern. And it was later repurposed it was made into this they removed one of the crosses and replaced it with this paraboloid antenna that stretches for about nearly a kilometer. And that is that nowadays is called the Molangle Observatory Synthesis Telescope. And this is one of the telescopes that I used a lot during my PhD and then research time later. But the marvelous thing about Australia is that, they're so quirky down there. So you have this beautiful radio telescope, and instead of hiring a lawnmower, they just let the sheep loose to mow the grass. And then there's the Parkes radio dish and the Australia Telescope Compact Array that I also use. So they have 5 dishes on a track. The track extends for about 3 kilometers. And then there's a 6th dish on a track not on a track, positioned about 3 kilometers away from the main track. And they can move that into, different configurations, but more on that later. The other thing about Australia is, as you all know, it has something like 10 of the 11 most venomous snakes on the planet. And so it was a regular occurrence that, you'd be leaving the control room and you'd be going down to just take a walk along here just to look at these marvelous telescopes, and you'd see a brown snake or something like that just wriggle by. And but the fun thing about it is that wildlife is abundant there. And so here you have these dishes of the compact array, and there's a little kangaroo that just goes hopping by. This is not my video, but I did see that. You saw it every day. So we've left the Reber with his 9-meter dish. We have Payne, Scott, McCready, and Pawsey with their Seacliff Interferometer. Time goes by. Engineers try to build bigger and bigger telescopes, and we have a really fine specimen here today, which is the Green Bank telescope, which is about 100 meters across, 300 feet across, and is there in West Virginia. And there's a similar dish in Germany, in Effelsberg, Germany, which is also 100 meters across. And I think Green Bank just makes it because Effelsberg might be elliptical, so it's not perfectly circular at the at the circumference, and so Green Bank just pips out the Effelsberg telescope. But there are challenges to building larger single dishes. And one of them is, simply physics. There's gravity. These things are difficult to keep up. It's an engineering challenge. An engine, maybe you can erect them, but then you have all these issues, with rotating them, and massive challenges. And weather is a challenge. All you need is high winds and things. They might not necessarily topple over, but it certainly doesn't make for receiving a strong and steady signal when you have your detectors waving about all over the place, like shaking about. So if resolution, if your goal is to obtain as much detail as possible of the target that you're observing in the radio sky, and resolution is directly proportional to or inversely proportional to the size of your detector, if we cannot build telescopes that are larger than about 100 meters across, how do we get the longer diameters to obtain better resolution? And the answer we already saw with Payne, Scott, and her collaborators, and that is to use interferometry. And that is when you bunch up a whole bunch of radio dishes all together into an array. And this is the iconic, now named Karl G. Jansky Very Large Array. It's in Socorro, New Mexico. And it consists of 27 dishes that can be moved by transporter along these 3 tracks, into 4 main configurations. And the most compact configuration, when all the telescopes are all bunched up together, it's only about 0.6 miles across. And the largest configuration, when you stretch the telescopes right out to the outer limits of their tracks, you get up to 22 miles, which is about 36 kilometers. So in effect, by linking up all of these individual dishes together, you get a telescope that is of diameter 36 kilometers across. However, there's a catch to this. It's not very simple to just add the signals from all these individual telescopes together. What you have to do is you have to take into account, here we have just a little diagram where you have a very simple interferometer that consists of only 2 antennae. And when you have the radio waves coming from outer space, you have from your target, you're observing a nice little quasar up here, and the radio waves come towards your antenna, and the signals, waves come down as like plane waves, and the signal will hit one of the detectors before it will hit the other. So you have to take into account all of these time lags between all of your antennae. When you have 2, it's a fairly simple, let's say straightforward operation. When you start to have 27 dishes, it becomes kind of complicated, let's say. And the more dishes you add, the more complex it gets to try to combine these signals so that you are time-stamping them. They all have the same timestamp. You are correlating these signals so you can get a coherent image of the radio source that you've been observing. And so this correlator here that is nicely represented by a neat little box here, this is what it actually looks like in reality. This is the correlator for the Atacama, the millimeter array that's up in the Atacama Desert in Chile. And here we see each one of these cables. Each one of these cables has a job in this endeavor. And so the more radio telescopes you bunch together, the more cables you're going to get. But it's so worth it. It is so worth it because here we've just mosaiced a couple of images. We have here on the left-hand side, these are the 4 main configurations of the VLA, and they are called configurations A, B, C, and D. There are some variants to this, but these are the main ones. So we're going to take a look at a quasar that's called Hercules A, and we're going to look at what do we see when we have the VLA in the 4 different configurations. So let's start with configuration D, which is the most compact. It's only about 1 kilometer across, so that's the 0.6 miles, the 1 kilometer across configuration. And when you observe in this configuration, you see the lobes, you see a little bit of the jets, and you see the lobes, and you see the sort of nebulosity of the lobes here. Then you move some of the antennae further apart, so you're in configuration C, which is now about 3 kilometers across. And you can start to see a little bit more detail. You see that the jets are a little bit narrower, close to the central source. And you see that there's some puffing, there's structure inside the lobes at the ends of the jets. And we move up to configuration B, which is 11 kilometers across. And now we're probing finer detail further inside of these jets, and you see the narrowness of the jets close to the central source, and really nice structure here at the outer lobes. And then when we go to the largest configuration, which is the 36 kilometers from end to end, we see exquisite detail here. And the whole point of this is that each one of these configurations is targeting a certain size of the detail in the source. And that tells you about the physics of what's going on in the source at these different scales. And so when you put all this together, you have this marvelous image. So this is the VLA. All 4 of those images have been superposed. And this here at the center is the Hubble image of the galaxy itself. So we see the nice optical galaxy here, and then with the radio jets that come out on either side. And I just love seeing these images put together like this. And I hope this shows the power of using the different configurations of a radio array. So, but why should we just stop at one country? You have the VLA right here, somewhere down here in New Mexico. Why stop at one country? We don't need to. We can spread radio telescopes all over the globe. In fact, we have okay, let's go back to one country. Let's go back to the United States. In the United States, we have this system called a Very Long Baseline Array, and it stretches from Hawaii to St. Croix in the Virgin Islands. And it is 10 25-meter dishes that are spread across the United States. And one of the VLA dishes is used, in fact, for a Very Long Baseline Array. And so when they're doing VLBA experiments, then that dish is out of commission for any VLA observations that might be undergoing at the time. And so effectively, the VLBA is a telescope that stretches from Hawaii to the Virgin Islands. The Europeans have a similar setup, and it's called the European VLBI network. VLBI is for Very Long Baseline Interferometry, and they have a whole bunch of radio dishes all scattered all across Europe. And there's the East Asian VLBI network as well. And this operates on exactly the same principle as the little diagram I showed of the two antennae receiving signals from outer space and then being correlated. But here we can correlate across continents. These telescopes can link up, and so you can effectively have a telescope that is almost the width of the diameter of the Earth. And that is exactly the technique that was used technique that was used by the Event Horizon collaboration. They released this marvelous image of the black hole in M87 in April 2019. And they linked up, they used radio telescopes from Europe across to the US, over to Hawaii, and down into South America. There's an ALMA that I mentioned before. So they were using the sort of test version of ALMA. And so they combined all of these telescopes together and to come up with this image. And I hope I can show you how. Our science editor, Camille Carlisle, had a lovely post on radio interferometry on our website, so you can go look it up. But here we have, am I going to be able to click this? Why doesn't it click? Is it doing anything? No. Huh. I wonder, I might have to show this to you later then. I'll just pull it out of the talk because I don't dare come out of this right now. Screen. No, that's not going to help me. Okay, I'll pull it up later then. Anyway, it shows how when you have these telescopes that are spread across the globe, and on top of it, the Earth is turning, how when you use the baselines, so each one of these telescopes links up with some of the other telescopes. They don't link up with all, but they have these, like this IRM will link up with the ALMA, and the ALMA links up with the with several here, and the JCMT over in Hawaii links up. And so each one of these pairs of telescopes provides a baseline, and as the Earth turns, these baselines then these baselines then cover the source, and like this, we eventually construct a picture. I would like to show that to you at the end of the talk, though. So I'll get back to that. But the question is then, how far can we go? You know, if we've already placed telescopes all across the globe, could we go into space? Yes, we could, and we have. There have already been a couple of successful missions. There's the whimsically named VSOP. That was, I believe it was a Japanese mission that was later named Halka. And then there was the Russian Spectre R that stopped operations only a short while ago, I think just a couple of years ago. And so Space VLBI has been producing some interesting results. And most interestingly is that the next phase of the Event Horizon telescope might be to lob an antenna either into Earth orbit or onto the moon somewhere. So I'll start summarizing some thoughts here. I personally am absolutely fascinated by radio astronomy, by radio telescopes. I haven't even gone into any of the radiation processes or any of the physics of radio, of the radio universe, which has its own fascinations. But in terms of just a handful of, let's say, successes that I and several of my colleagues consider to be successes in the world of radio astronomy. Of course, Jansky's pioneering work that discovered radio emission from outside of the Earth was really quite a groundbreaking result. And because for the first time, we were really looking at the universe in a new part of the electromagnetic spectrum. We weren't just relying on the visual part of the electromagnetic spectrum, but we were going beyond it. And in theory, I'd like to think that he basically launched multi-wavelength astronomy, which more and more people are engaging in now. It would be wonderful to be able to do it all the time, but there are all kinds of constraints, including time and accessibility and all of that. But it's with true multi-wavelength astronomy that we really can start to understand the underlying physical processes in these cosmic objects. And because the X-rays will tell us one thing, the ultraviolet will tell us another. And so just simply bringing in the radio taught us about the existence of quasars, about these powerhouses that are out there that are spewing matter at nearly the speed of light for hundreds of thousands of light years from the host galaxy. And so just being able to see in a different part of the electromagnetic, see in quotes, of course, different part of the electromagnetic spectrum was a massive achievement. And then, of course, one of the big results was the discovery of the cosmic microwave background, which was essential for understanding the Big Bang, the evolution, contents of the universe, and all of that. Of course, I would like to list a whole bunch of others, like the discovery of pulsars, Jocelyn Bell Burnell and her amazing work. And so the discoveries are many, and they are, I find, all monumental. And I'd also like to mention that the development of interferometry, aperture synthesis, that gives us superior resolution is also one of the big successes of radio interferometry, because without that, we would never have been able to image M87, for example, or do any of the other things that we've been doing. Challenges. There are many challenges, and among them, I mentioned earlier, building large dishes is a challenge. We had a marvelous telescope at Green Bank, so the precursor to the Green Bank telescope. So this is not the same one that I showed the image of just recently. And on November 14th, 1988, it looked like this. And on November 15, 98, it looked like that. So it too collapsed completely. And these are very sad, but they're a reminder that radio astronomy is very challenging, and the engineers who have come up with these novel solutions to try to observe the universe at radio wavelengths, that one has to take one's hat off to them. Other challenges that are a little bit more, let's say, serious are radio frequency interference. Unfortunately, there are only very few radio frequencies that astronomers are interested in that are protected. And there's a lot of pressure nowadays to allocate the so-called passive service, i.e. radio astronomy bands, to other usage. And even the protected bands that we can observe the universe in get disturbances from neighboring commercial use bands. And let's not forget, I mean, we might be using telescopes that are the size of the Earth, but we are trying to detect incredibly faint signals. They're very difficult to pick up. And it's a very tough job to try and hear those signals above all the noise that is around. And a friend of mine likened it to, you can't hear someone whisper if there's a party going on around you. And I thought that was a very illustrative phrase. So where do we go from here? Well, there are several monster arrays in the making. Among them, there's a square kilometer array that'll straddle 2 continents. South Africa, they're building a whole bunch or they're installing a whole bunch of radio dishes in South Africa and in Western Australia. And there are going to be thousands of dishes in the square kilometer array. The next generation VLA will increase the number of dishes from 27 to 244, and they'll all be of 18 meters in diameter. And the baseline will stretch 200 times longer than it is now. And we hope that one of the things that we can collectively do with all these instruments is, besides enrich our understanding of not just the radio universe, but the universe in general that we inhabit, But wouldn't it be exciting if we could get more VLBI imaging of other supermassive black holes, including Sagittarius A star, the supermassive black hole at the center of our own galaxy? So with that, I would just like to thank you all for your attention. And I hope I managed to make a little bit of sense. My brains are very much mashed potatoes at the moment. And I just want to conclude with saying that, not only do I love radio telescopes. A lot of people love radio telescopes, and they've also entered the popular culture with, of course, poor old Arecibo in GoldenEye and VLA in Contact. And there's a delightful Australian movie called The Dish. If you haven't seen it, I urge you to watch it, where the Parkes Radio Telescope features. And in case there's anybody out there who's interested, maybe you already are a member, but there's a Society of Amateur Radio Astronomers. And so if any of you is a member or you eventually get involved, I would love to hear from you at a later date. So thank you very much.
Well, thank you, Diana. That was fantastic. I already have some questions for you, if you don't mind.
Sure.
I marvel at our ability to detect Sag A star with simple radio telescopes. I didn't realize it was that powerful of a radio emitter to be heard from 30,000 light years away. That's pretty impressive. Well, A, that we could hear it at all, and B, that it's that powerful that think about how far away you get from a radio station and you can't hear it anymore. And here is a signal that's, going across the galaxy. So that's pretty cool. You talk about the challenges, and, I was going to ask about Green Bank, and of course, recently Arecibo bit the dust. One of our members recently gave us a short talk on his travels through Australia and mentioned that the Parkes dish is actually just sitting on the top of the building, that it's actually not bolted down to anything. It's just its own weight holds it in place. I still marvel at that. That's crazy.
I'm just going to try and pull up that image that I have of it, because I have it right there.
There it is, that big guy on the upper right.
Yes.
That is just sitting on that building.
Isn't that fantastic?
That's crazy. You would talk about high wind and wow, why doesn't that thing blow right off? I'd be scared to death to be inside that building or anywhere near it. That's a big telescope. That's a big telescope. And, one other thing I wanted, and that's the telescope that helped us to watch Neil and Buzz on the surface of the moon.
That's in fact what the movie The Dish is all about.
Oh, perfect.
So there's Parkes, and then not far from Canberra is another dish called in a place called Tidbinbilla. And I think that specifically I think that might have been the one specifically used when they communicated. And it has a little museum there as well. And they have all kinds of space memorabilia there. And it's really cute. And that's I think it's the same size as Parkes. It's absolutely massive.
I know, look at that. That's amazing. The other thing I was thinking about when you were talking about the early days of radio astronomy and the low resolution of the data. And I was thinking about how astonished must have the researchers at Jodrell Bank been the night that the moon occulted 3C273 back in 1963, when they realized that it was a point source on the sky.
Yeah.
Because back in 1963, the sky maps were pretty primitive, right?
Sure. Yeah, here I just pulled up again Reber's map. I mean, look at that. We have, we're going across from, this is galactic coordinates, but we're going from 0 to 90 here. And we're only seeing basically 3 sources when we know nowadays there are thousands or hundreds anyway.
Discrete sources. Yeah. I know probably every member of the club sitting here tonight has at one time or another watched the moon occult a star. And it's always pretty amazing to see how quickly the starlight is snuffed out by the limb of the moon. And again, I can only imagine the astonishment that must have been felt the night or the day that the moon did that to 3C273 in the radio part of the spectrum. That's fantastic.
Yeah, and that was what helped. Yeah, exactly. That's part of the whole 3C273 discovery story. In fact, that a lot
Sure.
of people don't know, like not too many know about that aspect of it. Yeah.
Well, it's and I can only imagine that how quickly they must have been on the phone talking to an optical observatory. I mean,
Right.
to watch for what came back out from behind the moon. And there wasn't
Yeah.
just one occultation. I think there were a series of them that they studied. But then they realized it was a point source. And
I think that was the work by Cyril Hazard et al. Oh, well, anyway, he took it up from there. Yeah.
okay, good. That's just
Yeah.
some of the fascinating things then, that we've done with radio astronomy over the decades. Pretty cool.
Yeah.
Well, there must be other questions. So again, folks should know how to unmute themselves. Let's let some questions go. I'll officially close out the meeting, but certainly you're welcome to stick around afterwards and kind of hang out with the crowd. So are there any other questions? There must be.
I raised my hand. I don't know if you.
Oh, I'm sorry, I didn't see it. Sorry.
I'm just curious, since you mentioned the Sagittarius A will be the next target, why didn't they start with that instead of M87, which is considerably further away? I've often wondered about that.
You froze for a second there, but I think I got your question. Though their first aim was Sagittarius A star. They did want to try to image that, but they encountered a few too many technical difficulties. And then they realized that they had a source that was more accessible, and that's why they turned to M87, but they're aiming to go back to Sag A star.
I think the angle also was better, more favorable. Instead of looking into the plane, M87 was flat on.
It was. I think that definitely had something to do with it for sure. But they're still sticking with their original plan. They're gritting their teeth. They're saying they're going to do it.
Hi there. Very nice talk. Thank you very much. I played around with a little radio astronomy when I was young. Made a few very tiny antenna. Didn't do too much, but I thought it was pretty cool. I'm curious about Arecibo. There's been talk that they just, with all the hurricanes and all the bad weather, that it just kind of fell into disrepair, and that's why it eventually just kind of rusted and fell apart. But it's such a natural parabola, and it just seems to make sense. Do you think anybody's would be willing to rebuild it? I mean, I know the Chinese have built a much larger version of it in a natural parabola there. I just was wondering if anybody, there's got to be some billionaire out there that might say, well, it's worth it. Or is it better to spend the money and put it up in space? Because, with Starlink and all the other things that are coming online now, the interference out there, it's not just visual astronomy that's going to be affected by all this. It's also radio. If it's not even worth rebuilding and putting the money somewhere else.
You ask very good questions, and I have to say that I don't know the answer to any of those. I wonder if this was a bit of a surprise when it happened, that maybe people haven't really thought ahead enough yet. So I honestly don't know. If anybody else knows, please do chime in, because I think most radio astronomers are still a bit in shock. And so I don't know if they've actually thought about looking forward, but I think I perfectly agree with you. Those natural depressions that sort of cradle these huge dishes that was amazing, innovative technology back in the day. And I think it's just a question. They're not very flexible for, like, a lot of these synthesis telescopes like Arecibo, like Molangle and so on, they have very little maneuverability. So you basically have to wait for the Earth to rotate to be able to do your observations. And basically you can only get targets that transit above. And some have a bit of maneuverability in that they can move the secondary focus a little bit so that you can get a bit of angle. So I think it might have been innovative back in the day to come up with a dish that was 300 meters in diameter. But I would imagine that maybe they would want to put the resources into arrays and, like you said, space. But that's just me imagining right now. I don't know the exact answer.
Diana, let me jump in for just a sec. You need to remember that Arecibo was built by the Defense Department, and its primary initial job was as a radar dish probing the upper atmosphere of the Earth. This is pre-space age, I believe, and you know, we kind of know that now.
Early 1960s.
Yeah, and so we think of it as being this incredibly valuable resource, and it was. The failure occurred in the cables, and the cables were augmented when they added the Gregorian dome, which wasn't all that long ago. It's been, I don't know the exact date, but it's like 15 years or so ago. And it cost a lot to run that operation. And so it became kind of the poor orphan. It was all, if you follow its history, it was almost shut down a couple of times.
Yeah, it was only saved by several groups of people that came in subsequent waves to just come and pull it out of the doldrums.
Exactly. And so if you fancy the notion of rebuilding it from scratch, all the things you said about, you know, arrays and being able to point at, Arecibo was never very good at spatial resolution, but it was quite sensitive. And there are ways to get that now. And I think your point, Diana, is exactly right, that you could take that money and spend it in a lot of, even within radio astronomy, do a better job elsewhere.
Sure.
I just, last comment, it was a great tourist attraction, and I think it was good for PR for astronomy. It's unfortunate that, you know, it had to go in a very Hollywood way, kind of like Musk's spaceship yesterday, but anyway.
It was also very good for Puerto Rico, not only as an icon of technological achievement, but as an employer, and it's going to be sorely missed in a part of, you know, a part of the world that has been hit hard, and could have used its continued existence.
I just want to, sorry, was Mark still there? I love the idea that you had a couple of antennae in, what was it, your backyard?
No, I built, it was a parabola, but it was a long parabola. I read about it, this would have been back in the early 60s. And so I built something that was basically like aluminum foil and wires, and I don't even remember what I was looking for back then. It just seemed kind of cool, and it was a great project. And, you know, I got involved in ham radio and kind of put the two together. And so, but like I said, I have no idea what I was even, I don't remember what I was trying to find, but it was cool.
Yeah. I love it.
Well, Diana, weren't the folks at Arecibo also not just listening with the antenna, weren't they? Though they were doing a nice job of pinging asteroids, right?
I know they were doing a lot of sort of radar type observations of these minor bodies, and so that, but I've never really delved into that much. But if Kelly knows, he can speak up.
Or I can say something about something.
Oh, yes, please do.
What it is true that Pettingill in the 60s did radar observations of Mercury, and actually determined that Mercury was in a 3-to-2 resonance state rather than synchronous rotation state. Okay, and that was a big deal. That made a huge difference in the dynamical astronomy.
That's right, neat.
Well, it was the radio astronomers wasn't it the radio astronomers that did some crude mapping of the surface of Venus?
Yes, that's also true. And
Yeah.
also Arecibo was involved in that too.
Sure,
The
sure.
big discovery was the 3-to-2 resonance of the rotation of Mercury with its orbit around the sun.
But it was even as late as like 1959 and 60, where they were pinging radio waves off of Venus to really determine its distance with great accuracy, which allowed for an even more accurate value of the astronomical unit.
Absolutely.
I mean, that was a fundamental problem for centuries, you know, the distance scale of the solar system and transits of Venus, you know, parallax of Mars, parallax of Eros. But it was the radio people that pinging signals off of Venus were able to really nail it down. That's pretty cool. It's pretty cool.
I had Gordon Pettengill speak to our club back in, I guess, around 1990.
Huh. That's fabulous. I didn't know that. That's pretty good. Any other questions? Well, if there are no other questions, at least right now, Diana, why don't you let me have the screen back and I will share my screen again and we'll officially close the meeting. I think I can do it just right here by telling folks that on January 7th at 8 o'clock, we'll be having our next quarterly board meeting, and I'll certainly send out invitations to you like I do for the regular meetings, probably on Sunday. And then again, as a reminder on Thursday, you know, the Sunday before the meeting, and then again on January 7th as a reminder. Everyone's welcome to attend the board meetings, but you sort of have to sit there silently, I think. And the next monthly meeting will be on Thursday, January 14th at 8 o'clock p.m. Our speaker is Dave Eicher from Astronomy magazine, and he's going to talk about galaxies.